Hi everybody, this is Dr. Bricker here with a description of the mechanical energy lab activity. So with this experiment, there's not a formal write-up. You just go through, fill out the data table, answer the questions, do some calculations. Okay, so conservation of mechanical energy, and just a little bit of an intro about this. The objective here is to verify conservation of mechanical energy. We're going to be looking at kinetic energy and potential energy. So by mechanical energy, I mean kinetic energy plus gravitational potential energy for this lab. And the second objective is to study the difference between conservative and non-conservative forces. So the force that we're really going to have in this lab is gravity, and it doesn't matter the path that the object takes. If the amount of energy you have at the end is the same, independent of path, then you have a conservative force. So we will have conservative forces in this lab, and we'll take a look at that. We're going to be doing a PHET simulation, more about that in just a minute. So take a look through the theory part here. There's a lot of good information. This will actually help you to solve answer some of the questions at the end. So as you know from class, kinetic energy is 1/2 mv squared measured in joules, and we've got gravitational potential energy, mgy, also measured in joules. So in this class we will use SI system of units, so joules are the unit of energy. Okay, so what we have here is conservation of energy. So the left-hand side of the equation, kinetic energy 1, kinetic energy 2, is equal to kinetic energy 1 plus gravitational potential energy 1 is equal to kinetic energy 2 plus gravitational potential energy 2. So energy just changes forms, and we'll see that in the experiment that we do today. So the simulation, it is a PHET simulation, and the first part we will use intro, so skate park intro. Second part, we'll build our own playground. Okay, so a little bit more about the first part here. So open the following link. So if you notice, I just do control-click and it'll open up. We'll open up the intro graph, choose the quarter, skateboard ramp, and then you can click bar graph, grid, and speed. And we're going to select the smallest mass to begin with. So let's actually take a look at that. Okay, so I need intro, and I'm going to choose this path here. And then I want to click a few of these, speed, bar graph, and I can put the mass to small. Okay, let me go back to the lab and see if I selected everything I was supposed to. Bar graph, oh, grid and speed. Okay, so I also need grid. Okay. So the grid, actually, the reason you need grid is then you can see how some different dimensions here. So from the ground up to the top of the skate path here is 6 meters, so I can figure out the height. Small mass corresponds to, I believe, 50 kilograms. We'll have to look back at the data table to see that. And here's the speed. So we go all the way up to 20. So each of these is 1 meter per second. 1, 2, 3, 4, etc., all the way back down to all the way back up to 20. So you can actually take the skater and put the skater wherever you want to. So here, that's about at the top. Now if we go too high, the skater is just in the air. Like, you don't want to do that. You'll just drop the skater. So go all the way up here. So the red dot is at 6 meters, and then you can let this go. And if you want, you could pause it, which I just did. And you can play it frame by frame. So play around with it. You'll have some fun with it. So you see there was a whole bunch of potential energy to begin with, not a lot of kinetic. And then as you go down the path here, we're losing potential energy. We're not losing total mechanical energy, though. We're losing potential energy because it's being turned into kinetic energy. And then you can see the speed here all the way at the bottom. Okay. Good. And then you can record those different values. You can reset this. Whoops. If you reset it, it takes everything away. But I'll just do that anyway. And then you can take the skater, put the skater up here at 6 meters, and let the skater go, and see how fast the skater is moving at the bottom. Now, you don't want it after the skater has hit the ground, so we'll have to, I've paused it. We can start back over here. Whoops, pause. And then play, frame by frame if you want to. And then you want to get the speed right before the skater hits the ground, not after the skater hits the ground, because if you do that, then you've got the normal force on the skater from the ground. So we just want the effects from gravity. Okay? Whoops. Make sure you put the mass back to small when you do that. Okay, so follow the directions. I'm kind of going through it a little quickly, but that's the way to do it. Okay, so back to the instructions here. So go through all these different parts. Small skater is 50 kilograms. When you slide it over to large, then it's 100 kilograms. Okay, so make sure you fill out data table 1A and 1B. So maximum height, you saw where you started from. You have to calculate the potential energy, get the final speed, calculate the kinetic energy. And then do the same thing for free fall. Free fall means not on the path, not on the track anymore, just dropping it, right? And then when you set the mass to large, it's 100 kilograms, then do the same thing here. Okay, and then you'll have some questions to answer. So 1, 2, and 3. Oops, there's a typo. And then the second part is dealing with a different track. So it's going to look something like this. You'll have a skater start here up at A, come down here, and then sort of be launched this way. So same simulation, but you're going to build your own track. So we'll click on this again, but we'll pick the playground one. And same thing, grid speed, non-friction, select the smallest mass. So you'll have to slide that all the way to the left. Let's take a look at that. Okay, so I did Control-click, selecting playground. So you can build your own track here. Let's do speed, grid, I think it said bar graph, and then mass to small, and for this part, no friction. Okay, and then you can use this. I just clicked on it and I'm moving my fingers over here, and you can build whatever kind of track you want to. So you'll have to build a track that looks similar to the one in the handout. So here's the handout again. Not this one, this specific one down here. So you can put the leftmost part over here. It looks like it's 6, and then move over one that way. Put this one at about 2 meters, and then count how many squares over you go this way, that sort of thing. So make the track look like this, and then just go through and fill out this data table. So you'll have to use the increment it by just frames to do this. You don't want to let the skater go and try to read this speedometer, as it's going full speed. Just click through it with this button. Let me try to build something kind of similar. I'm going to do it quickly, so you take more care when you build it, but I think this is starting at like 6, and you could move this graph around, I think. Maybe not. Okay. This is around 2. Again, I'm doing this quickly. You do it with more care. So we want to take the skater, no friction, small mass. You can put the skater up here. Again, you do this a little bit more carefully. Let me try to get the center right at 6 meters. Okay. Let it go. I'm going to pause and move them back, actually. Okay, so I think that's pretty close to 6 meters. And then you can go frame by frame, right? You don't want to do it at full speed and try to record the speed at these different spots. So we're starting from rest at 6 meters. This is position B, I believe. I'm going to lower it a little bit. And then go frame by frame, and you can record how fast the skater is going at position B. something like that. So you see how fast that is. And then at position C, which is right before the skater hits the ground. So not on the ground, right before the skater hits the ground. So we got a little projectile motion going on. And maybe one more. I'll leave it up to you to do that part. Okay, very good. Let's go back to the lab assignment here. So again, construct this track. Make sure that you have these selected. Actually, for this one, you don't need bar graph, just grid and speed. And we're starting at point A, which is 6 meters. We're going to see what's going on with the speed here at position B and a certain amount of height here. And then same thing here at C. So C is on the ground, so the height at C would be 0. Okay, and you want to get the speed again right before the skater hits the ground. And then there's some questions to answer here too. Calculate the ratio of mechanical energy at B to A and the mechanical energy at C divided by the mechanical energy at B. And what do these ratios tell you, and what would you expect from that? So think about that. Same thing, you know, a couple more questions here. I don't want to give too much information away. And then a couple of additional questions. Name 3 forms of energy. Pick whatever kind you want to. Define them. Difference between conservative and non-conservative. So I think from the intro to the lab, you should have a pretty good idea how to answer that one. And then finally, one more problem here. Okay, have some fun with it. You have a week to do it. No formal write-up for this one. It's just go through and answer the questions. Okay, I will talk to you soon. Bye-bye.